Welcome everyone to this sixth lecture, states of matter, gases and liquid. So in the previous classes, various laws of various gas laws like Boyle's law, Charles' law, and Avogadro's law. Further, we have also studied the ideal gas equation, and we have in the last class we have also touched upon the Dalton's law of partial pressure. So in this class, we are going to delve deeper into this Dalton's law of partial pressure, and based on that, we will solve a couple of examples, and then we'll directly jump into the kinetic molecular theory of gases. And from the kinetic molecular theory of gases, we are going to derive how these, or we are going to explain the various gas laws and their molecular understanding. Okay. Right, the first topic which we are going to study is Dalton's law of partial pressure. So this law was formulated by John Dalton in 1908. Formulated by 1808. It deals with the pressure exerted by a mixture of non-reacting gases enclosed in a vessel. So according to Dalton's law of partial pressure, the total pressure exerted by a mixture of two or more non-reacting gases in a definite volume is equal to the sum of individual pressures with each gas, which each gas would exert if it occupies the same volume alone at a constant temperature. Right? So the first point is that it deals with this law deals with the pressure exerted by a mixture of non-reacting gases, right? A mixture of non-reacting gases enclosed in a vessel. This law states that the total pressure exerted by a mixture of two more non-reacting gases in a definite volume is equal to the sum of individual pressures which each gas would exert if it occupies the same volume alone at a constant temperature. So to understand in detail, let us take an example. For example, P1, P2, P3, and so on are individual pressures of gases known as partial pressure. So P1, P2, P3 are the partial pressures, right? Then the total pressure is going to be total pressure, which is denoted by, let's say, P total of the mixture of gases at the same temperature is given by this term, that is P total is going to sum of the individual pressures, right? P1 plus P2 plus P3 and so on. Okay. And the partial pressure of each gas, means the pressure of gases, means the pressure at which that gas would exert if present alone in the vessel at the same temperature as that of the mixture. So in order to illustrate this, let us take an example, and further let me drag a picture so let us understand that this is the picture. So to demonstrate the law, let us consider three vessels, right? These are the three vessels, each of 1 liter capacity, right? So its volume is going to be 1 liter. Its volume is also going to be 1 liter, and its volume is also going to be 1 liter. Let the first vessel contain gas A. So this consists of gas A. This consists of gas B, and this consists of mixture of gas A and B. And the gas A is at a pressure of 30 bar, and gas B individually, pure gas B is at a pressure of 0.45 bar. Now, if we put both the gases A and B in the third vessel, so this is the third vessel, right? At the same temperature, then the total pressure in this, right? So then the total pressure of this gas is going to be nothing but PA plus PB, which is nothing but this 0.30 plus 0.45, which is nothing but 0.75 bar. So let us move on to the next topic. Partial pressure in terms of mole fraction, right? In terms of mole fraction. Mole fraction is a method of expressing concentration of a component in a mixture. It is defined as the moles of a substance in a mixture as a fraction of total moles of all the substances, right? What is mole fraction? So mole fraction is a method of expressing concentration of a component concentration of a component in a mixture. It is defined as the moles of a substance in a mixture as a fraction of total moles of all the substance. Total moles of all the substances, right? So let us consider if n1 moles of any substance is present and total moles of the mixture, then the mole fraction of component 1, which is denoted as x1, it would be given by x1 is equals to n1 by n, right? Let us consider, for example, we have a binary mixture. For example, for a mixture of two substances A and B having number of moles as Na and Nb respectively. Then their mole fraction is given by Xa would be nothing but Na by n total, right? So here it should be n total. Xa should be Na by n total, and Xb would be Nb by n total, right? But here what is going to be n total? N total is going to be nothing but Na plus Nb, right? Xa is going to be Na by Na plus Nb, and Xb is going to be Nb by Na plus Nb, right? So now let us generalize this, right? So let us suppose at temperature T, three gases are enclosed in a volume V. Three gases are enclosed in a volume V, and they exert a pressure of partial pressure of, let's say, Pa, Pb, and Pc respectively. Then what we can write is, assuming that the gases are ideal, we can write that Pa is going to be NaRT by V, Pb is going to be NbRT by V, and Pc is going to be NcRT by V, right? Where and Na, Nb, Nc are the moles component A, B, and C respectively, right? And as per Dalton's law, what we have is we should be having total pressure is nothing but Pa plus Pb plus Pc, and when we substitute, what we get is we get P total is nothing but NaRT by NaRT by V plus NbRT by V plus NcRT by V. Taking out RT by V as common, we get Na plus Nb plus Nc multiplied by RT by V, right? Now we are going to divide both the sides by n total, right? Hence, we are going to divide both the sides by P total, right? So let us assume that this is expression 1, this is expression 2, this is expression 3, and this is expression 4. Now dividing 1 by 4, right? And what we get is P1 by P total is going to be Na into RT by V divided by Na plus Nb plus Nc into RT by V. Therefore, P1 by P total is going to be Na by Na plus Nb plus Nc. This is nothing but Na by N total, right? It is going to be nothing but Xa. Therefore, P1 is equals to Xa times P total. P1 is nothing but Xa times P total. Similarly, we can show that P2 is nothing but XD into P total, and or let's say this is P1, this is PA, this is PB, this is PC is going to be XC by P total, right? And this is a very important. So in general, what we can write is, in general we can write PI is nothing but XI times P total. This is a very important expression. So here it's going to be PA, PB and PC, right? So it's going to be PA. So in general, so this is for in general for IR gas. Thus, if total pressure of a mixture of gases is known, then the above equation, like this expression, can be used to calculate pressure exerted by individual gases. Thus, the partial pressure of gases in the mixture is the product of its mole fraction and total pressure of the mixture, right? Hence, what we can say is, thus, if total pressure of a mixture of gases is known, then the above equation, then the above equation. So when we say above equation, that means this equation can be used to calculate the pressure exerted by pressure exerted by individual gases. Thus, what we can say is the partial pressure of gases is partial pressure of gas in the mixture is the product of its mole fraction. The product of its mole fraction and total pressure of the mixture. Let us solve an example based on this. What will be the pressure? What will be the pressure of the gas? Pressure of the gas mixture when 0.5 liters of hydrogen at 0.8 bar and 2.0 liters of oxygen at 0.7 bar are introduced are introduced are introduced in a 1 liter vessel at 27 degrees centigrade. So let us first understand what is being given to us. The partial pressure of hydrogen gas. Okay, so we are given, that is what we need to do. The volume is given as 0.5 liter. Final volume is given as 1 liter. Initial pressure has been given as 0.8 bar and P2 is what? So applying first Boyle's law at constant T and N, right? Which is nothing but P1 V1 is nothing but P2 V2, which implies P2 is nothing but P1 V1 by V2, right? Therefore, P2 is going to be 0.8 bar multiplied by 0.5 liter divided by 1 liter. Therefore, P2 is going to be 0.4 bar, right? Now, partial pressure of oxygen gas, right? So here we are given V1 as 2.0 liter, V2 as 1.0 liter, P1 has been given as 0.7 bar and P2 is unknown, right? So again we use Boyle's law, which is nothing but P2 is equals to P1 V1 by V2. This implies P2 is going to be 0.7 bar multiplied by 2.0 liter divided by 1.0 liter, right? Therefore, P2 is going to be 1.40 bar, right? So then total pressure is nothing but sum of the individual partial pressure, right? Hence the total pressure of the gas mixture, which is denoted as P total, is nothing but given by P total of partial pressure of hydrogen plus partial pressure of oxygen, which is nothing but which we just calculated, zero point 0.4 bar plus 1.40 bar, right? Therefore, total pressure is going to be 1.80 bar. Now let us move on to the kinetic theory of the kinetic molecular theory of gas. The next topic is kinetic molecular theory of gases. The various gas laws which we have discussed earlier were merely based upon the experimental observation. There were no theoretical background to explain them. The scientists have always been curious to know why the system is behaving in a particular way. For example, gas laws help us to predict what helps us to predict that when we compress gases, pressure increases. But what happens at the molecular level when the gas is compressed was an important and unexplored question. Right? So, in order to account for the observed behavior of gases, a model was proposed which takes into account molecular concept as well as kinetic concept of gas molecule. Right? As the name implies, this theory takes into account the particle nature of matter as well as the constant movement of these particles. Right? The kinetic theory is also known as microscopic model, right? So let us write this. This is also kinetic theory is also known as kinetic molecular theory, right? Kinetic molecular theory, which is also known as microscopic model, right? Microscopic model. Right? So right? Because these assumptions are related to the microscopic particle, right? And was put forth by this theory was put forth by Bernoulli. This theory was put forth by Bernoulli and was further developed and extended by Clausius, Maxwell, and Boltzmann, right? Clausius, Maxwell, Boltzmann, and other. Right? Now let us look at the postulates. Postulates of kinetic molecular theory. Kinetic molecular kinetic molecular theory. Okay. So the first postulate of this theory is all gases are made up of very large number of minute particles, and these particles are known as atoms or molecules. So all gases are made up of made of very large number of very large number of minute particles which are nothing but atom or molecule, right? The second postulate was the molecules are separated from one another by large distances, and the empty space among the molecules are so large that the actual volume of molecules is negligible as compared to the total volume of the gas. The molecules are separated from one another by large distances in the empty space among the molecules are so large that the actual volume of the molecules is negligible as compared to the total volume of the gas. Total volume of the gas. The third point is the molecules are in a state of constant and random motion in all the direction. During their motion, they keep on colliding with one another and also with the walls of the container and thus change their direction. So the molecules are in a state of ceaseless or constant and random motion all the directions. During their motion, they keep on colliding with one another and also with the walls of the container, also with the walls of the container and thus change their direction. Change their direction, right? The fourth postulate of this model is molecular collisions are perfectly elastic. That is, no loss of energy occurs when the molecules collide with one another or with the walls of the container. However, there may be redistribution of energy during the collision. Okay. So, molecular collisions are perfectly elastic, right? That is, no loss of energy occurs when the molecules collide. When the molecules collide with one another or with the walls of the container or with the walls of the container, right? However, there may be, however, there may be redistribution of energy during the collision. The fifth postulate is there are no forces of interaction, either attractive or repulsive, between the molecules at ordinary temperatures and pressure. They move completely independent of one another. Right? So there are no forces of interaction, either attractive or repulsive between molecules, between molecules, right? At ordinary temperature and pressure. That means they move completely. They move completely independent of one another. Right? Next is the pressure exerted by the gas is due to the collision of its molecules on the walls of the container per unit area. The pressure exerted by the gas is due to the collision of its molecule, due to the collision of its molecule on the walls of the container, on the walls of the container per unit area, right? And the last assumption, last postulate of this theory is the average kinetic energy of the gas molecule is directly proportional to the absolute temperature. Average kinetic energy of the gas molecule is directly proportional to the absolute temperature. Now let us look at the justification for the above postulates, right? So justification for the postulates. So for these are the following justification. The first justification is the first postulate, that is which was the all gases are made up of very large number of minute particles. This postulate is in accordance with the general particle or molecular nature of the matter, right? The first postulate is in accordance with the general particle, with the general particle or molecular nature of the matter, right? Second one is it is well known fact that gases are highly compressible and they also have the tendency to expand indefinitely. This fact clearly supports the second postulate, which was the second postulate was the molecules are separated from one another by very large distance, right? So when the pressure is applied, the intermolecular distances decreases, and as a result, the volume of the gas decreases. Further, the volume occupied by molecules is so small that it may be neglected in comparison to the total volume. For example, it has been experimentally observed that the molecules of gases like hydrogen and oxygen have volume less than 0.1% of the total volume of the gas. Right? So it is well known fact that the gases are highly compressible and they also have the tendency to expand indefinitely. These facts clearly support the second postulate, right? Second postulate. Second postulate. When pressure is applied, when pressure is applied, the intermolecular distances decreases. Intermolecular distances decreases, and as a result, the volume of the gas decreases. Volume of the gas decreases, right? Further, the volume occupied by the gas molecules is so small that it may be neglected in comparison to the total volume. Okay, so the third justification is it is common observation that smoke or dust particles in the air are in constant zigzag motion. Smoke or dust represents solid particles suspended in air, which is a mixture of different gases. These particles are colliding with the molecules of the gases, and their zigzag motion clearly shows that the gas molecules too have an identical motion. If the particles were at rest and occupied fixed position, then the gas would have had a fixed shape. However, this is not observed, right? So it is common knowledge, common observation that smoke or dust particles in the air are in constant zigzag motion. Smoke or dust is what? Smoke or dust represents the solid particles suspended in air which is a mixture of different gases, which is a mixture of different gases, right? These particles are colliding. These particles are colliding with the molecules of the gases, with the molecules of the gases, and their zigzag motion clearly shows that the gas molecules to have identical motion, right? The next justification would be the molecules are constantly moving in all the directions. During the course of their motion, they collide with one another and also with the walls of the container. During each collision, the speed and direction of the motion of the molecules undergo a change. However, the molecular collisions are perfectly elastic. That is, the total kinetic energy remains constant. In these collisions, energy may be transferred from one molecule to the another, but the total kinetic energy remains the same. If these collisions were not elastic, then there should have been a continuous loss of kinetic energy and ultimately the molecules would stop. But this does not happen, right? The molecules are constantly moving in all directions during the course during the course of their motion. They collide with one another, also with the walls of the container, also with the walls of the container. Right? During each collision, during each collision, the speed and direction of the molecules undergo change. Of the molecules undergo change. Right? However, the molecular collisions are perfectly elastic. The molecular collisions are perfectly elastic. That is, the total kinetic energy remains the constant. The total kinetic energy remains constant. In these collisions, energy may be transferred from one molecule to another. Energy may be transferred from one molecule to another, right? However, the total kinetic energy remains the same. Remains the same. If these collisions were not elastic, then there should have been continuous loss continuous loss of kinetic energy and ultimately the molecules would have stopped. But this does not happen, right? This does not happen, right? Right? So there are also a couple of more for justification for the postulate, right, which we will cover in the next class. So in this class, what we have seen the Dalton's law of partial pressure in detail. Further, we have also solved a couple of examples, and then we have understood the kinetic molecular theory of gases. We have understood the what is its needs, why was the need to develop such model, and then we have also discussed the postulates of this kinetic theory, kinetic molecular theory. Further, we have also seen the justification for all the postulates, for some of the postulates. The remaining postulates, we are going to study their justification in the upcoming classes, right? So in the next class, we'll complete this justification, and also we'll derive the ideal gas theory, that is the kinetic gas equation. Further, we'll also go into explanation of the molecular gas law models, which we have seen, like Boyle's law, Charles law, and Avogadro's law. Right. So I hope I hope that you have enjoyed this class, and I hope to see you again in the next class. Thank you.